correlation in multinucleon transfer reaction.
Okay, thank you, the organizers, for the opportunity to participate in this workshop. Today, the summary of my talk. First, I will talk about nuclear spectroscopy via transfer reaction between heavy ions, the oxygen 18 or 16 reactions, two neutron transfer reactions, using the coupled reaction channel method and two-step coupled reaction Born approximation and distorted wave Born approximation, applied to the 12 carbon 13 targets, oxygen 16, nickel 64, silicon 38 at 48 MeV. The experimental data of all these reactions were in Catania, in Laboratorio Nazionale do Sul. Then I will show some correlations into proton transfer reaction. I will pick on one example. That was the first experiment of the pilot experiment of the Numen project. I will then show the correlation between neutron and proton in transfer reaction, lithium-6 plus carbon-12, and lithium-6 plus fluorine-17. Then I will show some result for the helium-3 and triton transfer reaction in lithium-6, the unusual clustered configurations in lithium-6. Finally, I will talk about alpha clustering nuclei, transfer reaction, and evidence of alpha configuration using fusion cross-sections. Finally, the conclusions and perspectives. So all this started, we started studying the two-neutron transfer reaction, trying to explain why they were so, in many papers in the past, the people have to use a normalization factor very big, even, for instance, like this. Well, then the one that is shown in that table. They obtained very good, they described the shape of the angular distribution, but they needed a normalization factor in order to get the absolute value of the experimental data. We then tried to find what was the reason, and the very reason would be because those reactions were done at that moment when they're not big computers that we have right now. So the people use simplifications in the triton wave function. They use zero-range approximation for these nuclei that have very standing wave functions. They use only simultaneous transfer, don't study the possibility to have sequential two-neutron transfer reaction. And they did a lot of numerical simplification to solve a 6-dimensional integrals to determine the transitions amplitudes. Also, later, the triton was prohibited for safety reasons, and although the wave function of the triton is more simple than the oxygen 18, that is a core of oxygen 16 plus 2 extra neutrons, this appears as a natural candidate. Although it could be like helium-6, but helium-6 then is weakly bound. So for this reason, the helium-6 was used. So the theoretical method, the main ingredients in our calculations are the following. We use two-step exact finite range CRC calculations and two-step CCBA calculation or DDBI calculation for sequential transfers. We always use prior representation, complex Riemann. We include all the time the non-orthogonality corrections. For the optical potentials, we use the São Paulo potential. To derive the single particle or cluster wave functions, we use the Wood-Saxon 4 factors with the fixed radius and diffuseness, and we vary the depth of the potential in order to get the experimental separation energies. The deformation parameters are taken from systematics, so we don't vary any parameter. And the spectroscopic amplitudes needed in this kind of transfer calculation we obtain from Shell model, or interacting boson model, or interacting boson Fermi model, or QRPA, or semi-microscopic algebraic cluster model. So the coupled channel equation is the one that we have there. So it is obtaining if you expand the wave function in the basis in each partition, then you put in the Schrodinger equation, multiply, use the orthogonality in the same partition, and you get that equation. So for the single nucleon, you have to solve this equations, and the wave functions is the usual one everybody knows. The one that I want to make some additions is that the one that is what we call the independent coordinate model for the two particles. So we come from the two particle wave functions to the wave function of the relative movement of the two particles relative to a core. So we have this, instead of having these R1 and R2 components, we have the center of mass coordinate and the separation between them. When we can have this two-nucleon transfer reaction in one state, then we come from the initial state to the final partitions, or we can have through the intermediate partitions in two steps. In this case, we go through the intermediate partition that we are calling here gamma partition. The São Paulo potential is very well known, at least for the people here in Brazil. It's the one we use all the time. This potential have the advantage that we have a systematic for the matter density expressed in the two-parameter Fermi distribution. Fermi-Dirac distribution, that is, the radius is by this systematic and the diffuseness is fixed. So once we use this potential, we don't have any free parameter except two strength coefficients that could appear. So in all the optical potentials, in the final intermediate partition, we use these systematics that have been proved to, it is a good approximation to describe elastic scattering in the wide energy range. And in the initial partition, as we include some inelastic channels, and we are including also transfer channels, but not all the channels, we use a reduced strength for the imaginary part, as some of the channels we are included. So we can have a lot of very weak coupling states, but we have to account the loss of flux for these states, and this is why we use this 0.6 approximation. So one thing we can ask is, does the São Paulo potential systematics always work? Okay, for the nuclei near the stability line, it mostly works. But even for this kind of nuclei, like oxygen 18 that we are using here and oxygen 17, if you remember in the previous transparency, the systematic value for the matter density diffusion wave was 0.66. And for these nuclei have been proved through different calculations that this is a better result than the one that is proposing in the systematic. So the systematic is always a starting point, a good starting point, but we have to be careful with that. Here I show some examples for nuclei far from the line of stability, and here are the corresponding matter and charge distributions. The elastic scattering is not strongly perturbed by these changes, but if you look to the fusion cross-sections, for instance, for this neutron-rich nuclei, you see that the fusion cross-section, if you don't use the correct matter density, you will have completely different results. But I emphasize that nevertheless, the São Paulo potential is always a very good starting point to start the calculations. Then you want to do some refining, you can use Dirac-Bogoliubov matter density and put in the code and get better results. So let's go to the results for the different systems. We selected oxygen 16, as I already said, because Triton was prohibited for safety reason, and oxygen 16 can be interpreted as oxygen 16 core with very low polarizability, and we have two extra neutrons in the oxygen 18, whose wave function is quite well known. And the first paper, or in the first work, we have done not only the two-neutron transfer, but also the one-neutron transfer in this reaction that might populate the same state in carbon-14 final state. And we see, looking to the spectrum that I'm not showing here, we show only here the carbon-14, only to see that the states are very well resolved, that we can take the cross-section for all of these states, but the one that corresponds to one neutron transfer is not like this. It populates completely different states. That is already a signature that one neutron transfer and two neutron transfer populate completely different states. Here are the couple scheme used in calculation, so I will not show the details. The important thing that we are going to do all the time here 3 times calculation. The first one is we call a string cluster model. In this case, you disconsider completely the structure of the neutron cluster, and you consider that they have spin 0, so they are anti-parallel, and put the spectroscopic amplitude equal to 1. The second one is this CCBA method, that is for the sequential transfer. You pass through the intermediate partitions, so you consider the in infinite order the couplings in the initial partition, but the transition between different partitions is through the distorted wave-Born approximation. And the independent coordinate method, in this case, you transfer in one step also the two neutrons, but you consider the coordinates and the quantum numbers of each particle. So here are the results for the carbon, oxygen 18 plus carbon 12, giving carbon 14. You see that we could describe very well the experimental data, especially when we consider the direct transfer of the two neutrons, the sequential transfer that is represented. I use the same color of the model here in the figure. So the sequential one is lower than the direct transfer, so we see the clear signature of the correlation of the two neutrons. Then if we go to high excited states, we then look to the carbon-13 target. So we wanted to see if when we add one extra neutrons, this correlation is broken or is continuing, the correlation between the two neutron transfer continue to be valid. So here is the spectrum. We see clear peaks again above the one neutron separation. So we see a lot of states here that could be determining experimental, the angular distribution. We have to say that in most of the cases, although I'm not showing here, we compare our results with the TP reactions or PT reaction, and we see that we observe the same peaks that were observed there with the same characteristics. So we see we have a strong population of two neutron configurations, and also what we call the giant pairing vibration that I will not talk here. So here are the results. Again, the theory has the same color in the figure. So the low-lying states, the ground state, and the elastic scattering, and all the other the lower static states, we see that the cluster model overestimates. The microscopic independent coordinates when you transfer in correlated to neutrons describe very well the experimental data, and the sequential one again is slightly lower. The high excited states, we also see that the independent coordinates model is quite near the experimental data, and the two-step process again is lower. So we see a clear identification of the neutron correlation in this transfer reaction. Of course, even if the direct transfer reaction it has lower cross-section, this does not mean that you don't have correlation. You don't have correlation when you have many order of magnitude in one respect to the other. So in fact, both of them are important, but the most relevant in this case is the direct to neutron transfer reaction. Then we studied the nickel 64 target. This is the model space and the couple scheme used for the direct and sequential transfer. We first did calculation using the shell models as in the previous cases. You see here that in this case, the string cluster model is a very poor model, so, and it's expected because to say that you have two neutrons as a core in nickel 64 is quite not reasonable. And also, we observed for the ground state now that both models have about the same order, but now the first two plus state of nickel 66, the sequential one transition, two-step transition, is dominant over the direct correlated to neutron transfer. As we observed that we have no very good description of the experimental data, when we asked to our colleagues from, not Pavo, about pizza, well, the people that do interacting boson model and interacting boson fermion model to calculate for the spectroscopic amplitude to try to take better results. You see that in this case, when we do this kind of calculation that have already some collective ingredients in the calculations, you see that we now have that for the ground state that is spherical, not deformed, we obtain again that the direct transfer dominates over the sequential, but for the 2+ state that is already collective states of the nickel 66, there is a dominance of the direct transfer over the two-step transfer. Here the sequential transfer dominates over the direct to neutron transfer. Finally, we study a well-deformed nucleus already in the ground state, that is silicon-28. This is the model space used. In this case, we are in the middle in the two closest shells, so you need a larger model space, more complicated shell model calculation, but in the end, you can obtain quite reasonable result here. In the left, we have the result for the cluster model. Even if it is a light system, the cluster model overestimates the experimental data. It's not a good model. But we see that even for the ground state, for the first excited state, and here is a combination on some states that cannot be resolved experimentally. And of course, in the theoretical calculation, we put all of them together. We see that here already the sequential transfer dominates in all the cases, although the direct is not, you cannot say there is no influence at all. There is not present at all. So now I want to put your attention here in this table when the B2 values are given for all the systems are shown here and all that are available in the literature, and for which the people do this same of calculation considering the direct and sequential transfer of two neutrons. And we see that in the case when the correlation is dominating, this B2 is very small. In the case when the sequential one is dominating, the B2 is larger. So it is connected to the collectivity of the state. So when you transfer two particles, there are two particles that are contributing to the correlating more than two particles, not just the two particles. So the main contribution of the wave function of this state is not two particles, but more particles are contributing to that. So one can ask, but okay, we are looking for transfer reactions, but we describe well the transfer reaction, but from the output of this kind of calculations, you have also elastic and inelastic cross sections. So are you able to describe at the same time all the observables? So here an example for oxygen 16 for silicon-28, the last system I showed to you, where there were available the elastic scattering and the inelastic for the first state, and we did nothing else. So we just put the result we have from our CSC calculation compared with experimental data, and you see the very nice agreement. Of course, we have a lot of calculation for many systems involved in the Nuclei project for not only two-particle transfer, but also for up to 4-particle transfers. And with this methodology, we are always able, or almost always, you can never say always, but we are usually always to describe not only the transfer reaction, but also the elastic, inelastic, even sometimes the single charge exchange reaction. So the conclusion from this part is that we could describe the experimental data of transfer reactions for two-neutron transfer reaction using these models. When we add a one neutron, the correlation between the two-neutron transfer did not disappear. We see that we have a dominance of the direct transfer for nuclei that are not collective in the final states, and when we have collective excitation, they correspond to collective excitation in the final state, the dominance is of the sequential one. Then we come to the two-proton stripping reaction. This was the pilot experiment of the Nuclei project. It was oxygen 18 plus calcium 40, when they were trying to study the double charge exchange reaction. I am looking here only for the two-proton part because I could show the other part, but we see here that we have the same order of magnitude, not only the same, but even almost equal for the sequential and direct transfer reaction for the ground state transfer, and also for the first excited state of argon-38. So in this case, the final state are in some kind deformed, so this is no surprise. So we see again correlation even in two protons that we have column repulsions. Then for deuterium transfer reaction, I will show the result for two systems, lithium-6 plus carbon-12 and lithium-6 plus fluorine-19. Here we did three calculations because now you have deuterium, so you can transfer first neutron and then proton, or you can transfer first proton and then neutron, or you can transfer the proton and neutron if we want to call that deuterium in one step, using the same procedure we did in all the other calculations. And we can see that we could describe, it is written here preliminary result. They are not preliminary anymore, they are already published. I'm sorry for that. This was published in this publication. The experimental data were measured in the Tanner laboratory at Buenos Aires. So we did this calculation, and you see we could describe the two neutron transfer for the ground state, for the excited state, for different states. All these calculations, in this case, we have the sum of two states that are not resolved experimentally. And if we compare the direct transfer with the two sequential two variants, one proton and the neutron proton, for the two reaction fluorine and carbon, we see that in both cases the correlating proton neutron have a much larger cross section than the sequential one. So again, even this is of course, this does not mean that you will always have that the dominance channel will be the correlated proton neutron. It depends on the structure of the initial state and in the final state. So I'm just showing that we have this kind of correlation in this example. Here are the results for alpha transfer calculation in carbon 12 plus oxygen 16 at 20 MeV. The experimental data well available in the literature, even with some calculations that correspond to this black line. We did calculations considering two different coupling schemes that are shown here. And so the green corresponds to the green coupling scheme, and plus the red. And the red is only when we include this simplified model space. Both of them give good description of the elastic scattering, inelastic scattering, and transfer reaction, alpha transfer reaction. In this case, the spectroscopic amplitudes were calculated for the semi-microscopic algebraic cluster model by Peter Hess from Mexico, our collaborator. One important thing I want to show you here also, these are spectroscopic amplitudes calculated by a simple model, so shell model. You see that the difference is not that big. And even we calculate many things that is more difficult to calculate through this model. I'm saying that because in my next transparency, I will show you results for the helium-3 and triton transfer. That was the poster of Brenda. Some of you already have seen yesterday. In this case, we are looking for unusual cluster configurations in lithium-6. Everybody knows that when you look at the lithium-6, immediately you say it's a alpha cluster for a deuterium. So our colleagues from China, they measured relations, not the absolute value of this kind of transfer reaction, lithium-6 plus yttrium-89. In this case, you have the triton transfer. Here are the comparison between the extreme cluster model and the cross-section obtained for different states. When you use the microscopic model from shell model calculation, we calculate the spectroscopic amplitudes, and we see that the agreement with the experimental data is quite reasonable. Also, in the case of helium-3 transfer, we see that we obtain quite reasonable with the experimental data. Of course, I'm showing here that the extreme cluster model is a very bad model, because you will never say that you have in helium with a high probability helium-3 plus triton cluster. So that's for this reason the cross-section drops dramatically when you use the realistic spectroscopic amplitudes. We also did in this case comparison between the direct transition, because you say, okay, I have this final nucleus, but I don't know if I transfer a triton, or I transfer a deuterium plus a neutron, or a neutron plus a deuterium, or two neutrons plus one proton. So you have many combinations. We selected this one because in this case are involved only stable nuclei, so it's more probably that you get to the finished situation, because when you have unstable nuclei, in the middle maybe they decay before the second particle can be transferred. Maybe not, but at least it was our first approximation. So we see that the cross-section derived with the direct helium triton transfer is much larger than the sequential one in this kind of transfer. But when we look for the helium-3 transfer, we see that they are about the same. And the reason for that is the structure. When you look directly for which shells you are transferring, you will see that the spectroscopic amplitudes are completely different, and you get this kind of result. So the direct and the cluster sequential transfer are of the same order in the case of this reaction, and in the other one is completely different. So to finish my presentation, I would like to talk about the Fernandez poster yesterday, that we tried to find some evidence of alpha clustering calcium-40 by studying the fusion cross-section of calcium-40 plus zirconium-90. In this case, in the literature, the agreement in the literature, this pink curve there, is not a perfect like in the experiment in the original paper, because as I didn't emphasize on that, but we don't fix parameters. So we have the potential, we have the spectroscopic amplitude, and we put data and we compare with experimental data. So our agreement is not that perfect, but this is one channel calculation, the fusion from one channel calculation, and this is when fusion you get when you include the target states and the oxygen, and the calcium-40 3- states only. So with that, they all say, okay, we describe the fusion cross-section very well, and that's it. But if you look to the carbon-40, around this 3- state, you have a 2+ state and the 0+ state that has been determined as intruder state with a combination of shape coexistence and so on, okay? So we decided to include then this 2+ state and this 0 state. You see that when you include more states, the cross-section is going up and up. But the people, well, okay, that's good because I described experimental data and finished with that. I'm happy and so on. So what we decided, so in this case, we thought that this is because they were using not the correct structural model for the calcium-40. But it is well known that the calcium is represented sometimes as 10 alpha particles. Correlated somehow, this is very difficult to calculate, but it's like this. So what we did, we use this kind of configuration, so a core of argon-36 plus a helium-4 cluster, and did the calculation as one do in the cluster model calculation in continuous discrete acid coupled channel method. In this case, we don't need the continuum part because the separation energy of the alpha is about 7 MeV. So if you include the continuum or not, it will not make any difference in the fusion cross-section, okay? But we can include, using this cluster model, all the states, wherever we want, we can put one by one in this case. And at some moment, you will see that you put more states and you saturate. You don't increase more the fusion cross-section as is observed when you use the collective interpretation for the calcium-40. So we did this kind of calculation, and here, in the blue curve there, we show how the result for our parameter-free calculations, in which we just included a cluster model between the argon-36 and an alpha particle. Here is one transparency that Valdir Guimarães shows on Tuesday for this reaction, that is carbon-13 plus beryllium-9. This experimental data, again, is from Tandar, a collaborator from Argentina. And we see that here there are many channels, elastic, inelastic, boron-11, but you have even here lithium-7. And one can wonder, what is this? Is a lithium-6 transfer? Or is it alpha plus deuterium transfer? Or is it deuterium plus alpha transfer? So at the moment, I don't have an answer. I just can tell you that the week before than this, I were in Sao Paulo. I asked to Waldi, do you have the angular distribution for that? And I put a simple model there, consider the lithium-6 transfer. From my surprise, when I put a very low spectroscopic amplitude, I even still overestimate the experimental data. So it seems to be that it's lithium-6 itself. So I'm not saying that it's still this, it's just a comment for what we always think that it's impossible. But in my mind, I would never imagine that this kind of transfer could happen. This is important because when we want to produce super heavy elements, we have to try to find a lowering of the fusion barrier. Maybe when you transfer some heavy cluster like this in heavy nuclei reactions, maybe you first transfer something, you lower your barrier, and then you produce a fusion after that. So this may have some implications in the production of super heavy elements. Of course, this has not been taken into account yet. There is a paper recently published by the Australian groups saying something like this too. So with this, I don't know if you already told me that I have to finish, but I'm finished my summary. We have shown the relevance of the 2-neutron, 2-proton, and PN correlation into particle transfer reaction. The nucleon correlation are responsible for unusual cluster configurations in some light nuclei. Also, alpha cluster extrusion may be very important in describing the reaction mechanism for N-alpha nuclei. That's all. Thank you very much for your attention.
Thank you very much for this nice presentation. Question for Jesus? Tobias.
Lubian, very nice everything you said. I mean, going back to the work of Fernanda,
Yeah.
that is puzzling me. Yes, I mean, you have this bound state as a projectile of argon-36 and helium-4, 7 MeV of separation energy. So, I mean, this state should be pretty small. So the alpha and the argon will be overlapped. So probably for the bound state, you have to take into account more details. But as the result is very good, should have a physical reason. And I was wondering how we could see that, because maybe for the initial state is not important, but once you break up this guy, that potential should be good to describe in some way this process. Can you give some physical hints?
Okay, this is exactly the same process as I say you use in the CDCC calculations to calculate breakup. The problem here is, as you said, the binding energy is so high that if you put the continuum or not, is completely irrelevant because they will not affect not even the elastic, the inelastic, the fusion. That's why we didn't put. When you have a binding energy above 4 MeV, you already don't see. You can see some effect, static effect, because you can see some cluster model. You enlarge the wave function of your ground state, and this will produce some enhancement or decreasement of the elastic scattering, enhancement of the fusion cross-section, but just because of the cluster configuration, not but the dynamic part that is the continuum part. This will be important when you have very low separation energy, like in lithium-6 or lithium-11 or beryllium-11, or the one that have, let's say, at least less than 4 MeV. But I would say more than that. Important, you will see when you have about 2.5 below that, then you will see some effect, dynamic effect on fusion or in elastic. I didn't show here, but we also show for all the observables, not only the fusion. We saw also for the elastic, inelastic. Not for this system, there is not elastic and inelastic, but there is for other systems. They were in the Fernanda's poster. So we have also elastic and inelastic states of calcium, the angular distribution. If you use that collective state that describe this fusion cross-section there, the pink line, then you overestimate the inelastic, the backward part of the elastic, you also overestimate. If you use this model, you describe also at the same time elastic, inelastic, everything. So that's important. We always wonder that we don't want to describe only one channel. We want to describe at the same time with the same coupled channel calculation all the available observables or experimental data, because there was a discussion yesterday about the observables, the experimental data. Okay?
Yeah, maybe a question to the last plot you showed, or the
This
second
or
but
the
last. No,
previous
the
one?
next one. I think the next
okay.
one, where you had this lithium transfer, the lithium-6 transfer. I mean, there may be many ways to produce a lithium-7. Yeah?
Yes.
So
yes.
how you are sure, or why you are sure that
I
this
am
is
not
a
at
lithium-6
at this
transfer?
moment. This is what I said. I was surprised that when I put just a toy calculation, not serious calculation, I said, okay, I will use my potentials I always use, but I have no way to calculate the spectroscopic factor for lithium-6 transfer. If anyone know how to do that, please tell me. Because maximum we have to see doing that is 4 particles, two protons, 2 neutrons, or 3 protons, 1 neutron, like this. For that, one have to go I think it's almost impossible in initial model. Maybe in other models, interacting boson model, QPA, I don't know. But I said here that this could be not alpha, but can be also alpha plus deuteron, or deuteron plus alpha, or a lot of channels. So we have to, for all these channels, we can calculate the spectroscopic amplitudes. We can calculate the other one, and then give us a free parameters. The only thing I want to say is that I put a very small spectroscopic amplitude when I did this calculation, like say lithium-6 cluster. And I obtained the order of the magnitude, and for me this was a surprise, because I expected to have a very low cross-section for that.
Yeah, I mean, in principle, the proof would be if you can detect the nitrogen 15, or at least gamma rays from the nitrogen.
Yeah.
This is impossible to detect them directly, but maybe in principle there will be a way at some point to measure gamma rays from the nitrogen
gamma
15
particle
to
coincidence.
identify them.
You're right. Yes, I have colleagues that do this kind of measurement also in Legnaro, and they have a very good, there are Italians here that can support me, that they have a good particle gamma coincidence measurement. So now for me this is intriguing. I just want to put a comment. I'm not saying that what I said, that lithium transfer is a truth. I just a provocation, let's say.
Coming back to this alpha cluster calculation, may I conclude that the reaction mechanism is an isoscalar interaction between the two fragments, between two nuclei?
Yes.
It's a bit surprising. You would assume that the Coulomb force will be more important, right? Or this is too naive?
Well, in fact, in the interaction potential, we include both terms. So the Coulomb, always the Coulomb, and the nuclear part. And the interference between them is present also in the calculations. So there is no only this or this. Sometimes when we want to study which one is dominant, the only way we have is to take off one and remain one, and then the opposite. And then you can see, okay, if you sum both contributions, you will see you will have more than a combinate, because there is interference between them. The only thing you can say which one is more important, and if the interference between them is relevant or not. But in principle, only in the perturbative case you can separate both components. But usually when you have this kind of coupled channel calculation with strong couplings, you see the effect is huge. So the perturbative theory will not work here.
Thank you.
Okay.
Okay. Let's thank Lubian again. We can take more questions in the afternoon.